All right, I promised a review session. We're going to go through the practice test as the best thing I can do as a review session. Sorry, this is not a little more fancy like some of the things I did in the past, but these questions are going to be definitely representative of what's coming up for our test coming up real soon. So how many moles are there of an ideal gas at 237.15 kelvins, a volume of 12 liters, and a pressure of 2.01 atmospheres? Now the equation we need here, which is given on the back page of the test as always, is the Pivnert equation. So we have PV equals nRT. And it might actually help you to prearrange the equation to isolate N. N, remember, is the number of moles. So we've got, in the algebra, we've got N equals, let's see, PV divided by RT. I like to do that because it kind of helps guide me as to what I'm supposed to do in terms of the setup. So we're going to start with the pressure, 2.01 atm. And then times the volume. My pen's acting a little weird here. It's a little slow. 2.01 atmospheres times the volume, which is stated to be 12 liters. And then times 1 over, because the R is on the bottom here, so I need to put this little placeholder 1 on top. And given on the back page of the test is the value for R, but you probably memorized it by now because this is used so often. And that's liter atmosphere mole Kelvin. And then finally times 1 over, once again, because the temperature is on the bottom. The stated temperature is 237.15. Now I'm going to do a double check, make sure all the units are correct. So we've got atmospheres, that's going to cancel with this atmospheres. Liters, going to cancel with liters. Kelvin, believe me, it's going to cancel this Kelvin. This mole is going to end up top, and that's exactly what we want. So everything is set up and ready to go. So I'm going to get my calculator and do this real quick. All right, so I'm getting a value with sig figs in mind. I've only got 3 sig figs to work with. So 1.24. I was about to write kelvins, but that's incorrect. We're looking for moles, so it's moles. Okay, so we used the Pivnert equation to solve for moles. We had values for the pressure, the volume, temperature. R is always known because it's a constant. The only thing we didn't know is N. Did a little bit of algebra, prearranged the equation to isolate N, plugged in the numbers, and we got our answer. Now the next question, we're not going to use Pivnert this time. We're going to use, well, it looks like when I read this question, a gas initially has a pressure. Initially is already a key word, meaning I'm going to use one of those P1, V1 type equations. And initial is stated, but then final temperatures are given and stuff like that. So I'm already thinking that it's, since we have temperature, volume, and pressure, we need the whole tamale equation, which is this one. This one has all the variables involved. The only thing we don't know is what the final pressure of the gas is. Final being a keyword for P2, final pressure. So what I'm going to do here is I'm going to prearrange or pre-isolate the P2. And to do that, I'm going to keep the left side the same. So I'm just kind of reversing the sides here, but P1, V1 over T1, that stays put. But what I have to do to this side to isolate P2 is I have to divide both sides by V2. So that the V2 comes down here in the division. These cancel out. And I got to do the same thing on this side. So V2's here. And then I got to multiply both sides by T2. That cancels these out here. And I'm left with T2 up top. Okay, so putting in all the values, the initial pressure is 1.2 or 0.2 atmospheres. I'm fighting a cold here. Sorry about my voice, but I'm doing the best I can here. So 31.12 liters. My pen is really not working well today either. It's really stuttery, hence the bad writing. Sorry about that. And then times T2, which is stated to be the second temperature, which is 343.40 kelvins. Some sort of weird lag with my pen today. Okay, then on the bottom, we've got the initial temperature, which is 285.23 kelvins. Come on. And then times the second volume, which is 11 liters. Okay, so once we've got P2 isolated, we've got this expression right here. We plugged in the values, and then I'm going to go off screen here and calculate this real quick. All right, so hopefully I've done this calculation correctly. So I've got, with sig figs in mind, I've got 3 sig figs to work with, 3.47 atmospheres. The pressure went up in this case. Okay, so that's this can be quite challenging. You got to really know your algebra to do things like this. But if you're comfortable with algebra, this shouldn't be a big deal. The only thing to watch out for is I won't necessarily give the temperature in Kelvin, so be careful. If I give the temperature in degrees Celsius, you're going to have to change that to kelvins by adding 273.15 to the temperature. Same is true up here. Watch out for the units here. It's got to be atmospheres, liters, and kelvins. Otherwise, R's units are not going to cancel properly, so make sure you convert everything as necessary. We didn't have to do that in this case, but I don't make any promises for the actual test. So watch out for units, make sure they cancel properly. Now the next question is, I've got 3 gases mixed together, so I have a lot of experience with this. As soon as I see that statement, I'm thinking Dalton's law of partial pressures, which refers to gas mixtures. That's exactly what this is. So the total pressure of a gas mixture equals the sum of the partial pressures for gas A, gas B, and gas C. Now we're given the total pressure. We're also given the partial pressure for A and the partial pressure for B. And if you want to do this again, we can pre-isolate partial pressure C, which is what we're after. P sub C equals the total pressure subtract partial pressure A, subtract partial pressure B. And again, that's algebra, so make sure you pay attention to your algebra, or hone your algebra skills before coming to the test, because there's going to be a lot of algebra in this test. These are all additions, so we have to subtract them to get the proper algebra going. All right, so I'm going to set this up now finally. So the total pressure, ATM, subtract P sub A, and then subtract partial pressure of B. Now watch out for your sig figs on this little calculation. The setup is pretty straightforward. It's the sig figs that'll probably get you. Remember, the rules are different for subtractions and additions, so we're going to go, looking at all 3 of these numbers, the fewest digits past the decimal point is 2, so whatever happens, we're going to have to round our answer to 2 digits only past the decimal point. Okay, so 2 digits past the decimal point, 1.27 ATM. Okay, so we've got 3 gas law problems that we just solved, and everything's looking pretty good. I hope I got the right answers to everything. I'm going to scroll down here in just a second, but I need to clear the screen first before I do so. Okay, just a couple of quick multiple choice questions. Which of the following, or which of these molecules has the highest boiling point? And what we need to consider here is what has the strongest intermolecular forces. And just looking at this first one, C2H6, there's only carbon and hydrogen. So immediately I conclude that there's only dispersion forces, which is the weakest force. And that's it for that one. Same goes for this one, only dispersion. And so I'm already thinking that these are going to be the lowest boiling point. Now this one, just so you know, if you were to expand this out, it's got a tetrahedral shape. I probably should be drawing the bolts and dashes and wedges, but well, I guess I could still do that. So here's a bold like this, and this is dash. It's going away. But it's tetrahedral, and there is an overall dipole for this, which starts at the carbon, points towards the chlorine, and that's a local dipole, but that's also the overall dipole. The CH bonds don't really count for anything, but this one has dipole-dipole forces because of this permanent dipole and dispersion forces for sure. But I think we do better even with this one, which has hydrogen bonding. And I said in class that something that has hydrogen bonding also has all the forces. So this one's going to be higher than this one. And then this one's still higher. This is the highest one right here. This is the answer. Because it's got 2 carbons. It's a bigger molecule than this one. They both have hydrogen bonding to all the forces, but this one is bigger. So this one definitely has the highest boiling point. So when these substances are at the same temperature, which substance has the lowest vapor pressure? The one with the lowest vapor pressure is going to have the strongest intermolecular forces, which we already said is this one. So that is the lowest vapor pressure if they're all at the same temperature. Which statement about ideal gases is not true with regard to the kinetic molecular theory of gases? And I'm just going to go through these. Collisions between gas particles are elastic. We assume that, so that's true. There are no intermolecular forces of attraction. That's true for sure. Bigger molecules have larger volumes at standard temperature and pressure conditions. This is false. Okay. In this theory, we actually consider all gas particles to be exactly the same size with no volume. So bigger or smaller, it doesn't make any difference in this theory, so that's not true. Pressure results from the collisions with the walls of the container. That's definitely true. Temperature is a measure of the relative kinetic energy of gas particles. That's definitely true. Okay, so just a couple of quick multiple choice questions, which mostly have to do with gases, but also intermolecular forces.